In this example, we're asked to repeat an argument that we've used in our notes to find a formula for the sum of the first k cubes. The argument that we're going to use is we are going to use this formula for the telescoping sum with the particular sequence of a sub n equals n plus 1 to the fourth power. And we're going to evaluate this sum two different ways and eventually be able to solve for a formula for the sum of the first k cubed numbers, the first k cubes. So before we start this, let's write down a lemma. So this lemma is going to be used much later in the proof. Once we get to a certain point, we're going to have to apply this. But the lemma is that I want to state here is the sum of the first k terms where n is not cubed, but we start with just, there's going to be three different statements here. And we've proved these in the notes or in exercises throughout this course. So the first one is if you want to sum from n equals 1 to k the number 1, so this says to add up 1 plus 1 plus 1 k times, then that adds up to k. That one's pretty straightforward. The next one says that if you want to sum from 1 to k the integers 1 plus 2 plus 3 plus 4 all the way up to k, then this sum is equal to k times k plus 1 all divided by 2. There's a couple different ways to prove this. It's done in our notes, and you've probably done it before in a calculus class as well. So the third and final formula that we're going to need to use as a lemma is the sum, and it goes from 1 to k, of the first k squared numbers. So this is 1 plus 4 plus 9 plus 16, etc. And this one adds up to k times k plus 1 times 2k plus 1, all divided by 6. All right, and so this was an exercise in our notes. It's worked out by John Hammond in those notes, so this is a good one. Make sure you understand how to do this one before you try to watch this video, or before you try to attempt this example that we're going to do on our own. But we're going to need to know all three of these results to actually solve for this result that we want to know. All right, well, let's get to it. So I'm going to draw a line here and start the proof. I'm not necessarily going to structure this as a proof, a formal proof, but what we're going to do is we're going to compute this sum. So on one hand, we're going to compute the sum, n goes from 1 to k, of this a sub n minus a sub n minus 1. All right, this is called the telescoping sum, and this formula is worked out. The reasoning for this, the reason for this result of this sum is worked out in our notes. But we are going to apply this sequence itself into the series. So the series that we're actually looking at is the sum as n goes from 1 to k of n plus 1 to the fourth power minus n minus 1 plus 1. So here we're going to plug in n minus 1 for the n up here, and that just leaves us with n to the fourth power. All right, so this entire thing is inside the sum. And just by using this as recognizing that this is a telescoping sum, which is how we built it, right, then we can apply this result. So the result is going to be that if we plug in the upper bound, k, then this will be k plus 1 to the fourth power, minus, we're going to plug in 0 for n, but it goes into our sequence here, right? So when n is 0, this just gives us 1 to the fourth power. All right, and so this part right here is by the telescoping sum rule. So by telescoping sum rule. Now, to get a better idea of what exactly this is saying, we need to multiply out this first term, and this is a binomial theorem, so you hopefully have learned this in calculus. But this can be expanded out pretty straightforwardly. If you don't believe what I'm going to write down right now, then you should work it out, pause the video, and make sure that you agree with what I'm writing down. But I claim, by using something called the binomial theorem, that this is equal to k to the fourth plus 4k cubed plus 6k squared plus 4k plus 1. So all of this is a result of multiplying this out, all right, by the distributive property. So you can check that. And then we just have this minus 1 here. And at this point, these two are not only the same, but they're adjacent, right? So they're right next to each other. Those are going to cancel. And what we're left with here, but we should write this here. So this is by something called the binomial theorem. Again, if you don't believe this, if this isn't just obvious to you, you should pause the video and either work it out or go look up the binomial theorem and make sure that you agree with this. And so what we're left with then is k to the fourth power plus 4k cubed plus 6k squared plus 4k. So on one hand, that is the sum of this series right here, n to the plus 1 to the fourth power minus n to the fourth power, summed from 1 to k. All right. On the other hand, what we could do is we could use our binomial theorem and we could expand this term out first before we actually do the summation. So let's do that. I'm even going to write here, on the other hand, let's see what we have. Our sum, n goes from 1 to k, of this difference, n plus 1 to the fourth power minus n to the fourth power. Again, this time I'm going to expand this out before applying the sum, the summation. So expanding this out is very similar to this one, except the k's become n's, right? That's the only difference here. But all the terms are going to be the same. Again, you've already hopefully justified that you believe this one. So this will become then n to the fourth plus 4n cubed plus 6n squared plus 4n plus 1, and then minus n to the fourth. That term is just there. And this time something cancels, but it's not the same as what happened up here. So this time we have an n to the fourth and a minus n to the fourth, and before we even apply the summation, we can cancel those out, right? So those don't need to be there. They cancel each other out. And at this point, what we can do, I don't need to write this out here, but what we can do is, this is a finite sum, right? K is a finite number. So this entire finite sum can now distribute to each of the terms that it's going to apply to, and it's only going to apply to the terms that have an n, or in this case it's going to apply to the constant itself. But what we can do is distribute this out and factor out these constants. And so we can write this then as 4 times the summation 1 to k of n cubed. Now just pause for a moment. This term is exactly what we want to solve for, right? So to be solved for, TBS, to be solved for. All right, and then as we continue, we see we have 6 times the summation, n goes from 1 to k, n squared, plus 4 times the summation, n goes from 1 to k of n, plus the summation, n goes from 1 to k of just 1. So leave the 1 inside because it's, if you factor it out, it would just leave a 1 in there anyway. So that's the best we can do. And at this point, we now need to use what we called our lemma. And so our lemma applied to these three summations, right? It told us what these three summations add up to. All right? And again, these we should have proved either in the notes or in a calculus course or in an exercise of the notes. So these three can just be plugged in. So we're going to assume that we know these. That's why we're calling that a lemma. And I'm going to scroll down so that I have room. This one, remember, is what we want to solve for, right? So 4 times this sum just stays here. This one's always going to be here. That's our job, to find that one. Plus this is now 6 times, remember the summation of the squareds is k times k plus 1 times 2k plus 1, all divided by 6. The next term is 4 times the sum of just the n terms, so 1 plus 2 plus 3 plus 4. That one adds up to k times k plus 1, all divided by 2. And then finally, when you add all this up, this just leaves us with a k, right? Sum of 1 to k. And before we do anything else, we can do some cancellation, right? We have 6 over 6 here. Those will cancel. This 2 cancels 2 of these, right? And then we can combine like term, multiply this out and combine like terms here. So let's see what we have. Again, here's our 4. Sum n goes from 1 to k of n cubed plus. If you multiply this out, this gives you 2k cubed plus, so this k can just be brought in, right? Or you can multiply these out first, but you're going to end up with 2k cubed plus, there's going to end up being 3k squared plus k, simply a k. Here you end up with plus 2k squared plus 2k. After you have the 2 here and you distribute this out. And then finally we have a plus k here. And now I'm going to combine like terms on this one to just kind of simplify the way this looks. So this is the sum, 4 times the sum of n cubed, plus, this is the only term with a k cubed, so 2k cubed, plus k squared, we have 5 of them, right? So we have 5k squareds. And then the k's, we have 4, so plus 4k. And at this point, we have now computed our sum 2 different ways. Now, again, this term is unknown, and that's what we want to solve for. That's part of the answer to our original sum. But if we scroll back up, we see this right here is another answer to the same sum, right? So that what I just outlined in the green box, must be equal to all of this, because they are both answers to the same sum, right? They're the answer to the same sum. So what we're going to do next is set those equal to each other and solve for this term that we actually want to know. All right? So that's our last step here. So setting these equal, we obtain. On one hand, I'm going to rearrange this. So as we set them equal to each other, remember our goal is to solve for this sum of n cubed. So I'm going to move the other terms over, so there's going to be some subtraction on that side. But when we set this term equal to this one, right, then these terms will be on the right hand side, they'll be positive, and then we'll move over these terms to make them negative. So our sum is going to look like 4 times the sum that we want, n goes from 1 to k, of n cubed. It's going to equal, again, before we move those over, let's write this term. So this one's k to the 4th plus 4k cubed. So plus 4k cubed plus, what was it, 6k squared plus 4k. Make sure you copy this stuff correctly, because if you make a mistake in your copying, then you're going to get a wrong answer to your summation, of course, right? And so now we have to subtract off these last three terms. So we're going to subtract 2k cubed minus 5k squared minus 4k. And immediately we see that the 4k's will cancel, so that term is gone. All right, and then we can combine the like terms of these other ones. So we have 4k cubed minus 2k cubed. That's going to leave us with 2k cubed. And we have 6k squared minus 5k squared. That's going to leave us with 1k squared. All right, and so let's see what we have here. This ends up being, we still have our 4 over here. We'll have to take care of that in a minute. This is going to be k to the 4th plus what? What did we say? 2k cubed, and then plus another simply k squared. All right, and this side we want to try to factor now. So this one can be factored out. We can take a k squared from everything. There's two k's in everything here, and we're left then with k squared plus 2k plus 1. And this is, of course, a perfect square. So this can be written as k squared times k plus 1, quantity squared. Make sure that works out right. And at this point, we can then divide by 4, and we will have our formula. So this is a sum 1 to k, n cubed. It's equal to k squared times k plus 1 squared, quantity, all over 4. And this is exactly the right formula. It might not be exactly the way that you've seen it, so hopefully you've seen this in a calculus course. Maybe you didn't prove it, but this is a formula from a calculus course that you should be familiar with. And usually it's written in the following way. So it's written with large parentheses, k times k plus 1 all over 2 quantity squared. Either of these is totally fine, right? They're completely correct ways to represent the sum. They're equivalent, right? But sometimes it's written this way, or usually I should say it's written this way, because this sum inside of the quantity squared should look familiar. It is the answer to the sum from 1 to k of just n terms, right? So when you make it n cubed, you square this term. It's easy to remember that way. But the reasoning for that is not so clear until you've worked out all of this proof, right? And so there's a derivation of the formula for the sum of the first k cubes. Pretty clever proof, and I hope you enjoyed it.